Now keep in mind that Seamless does not give you exact time control. So when the timer fires, it will reset the explosion via the uniform, the time value. It will generate new vertex data, but there's no guarantee that these things happen simultaneously. So especially if you have a lot of points, the time may be reset first, and then after some milliseconds the vertex data that change. So if you want this kind of precise control, you should go beyond seamless signals, which are rather simple, and use some kind of library that integrates event streams and things like that. But for now it is just fine. So the next step is to make these square points circles. In OpenGL this is actually surprisingly difficult. I don't know any parameter, or not even a very long parameter, that will render your points as circles. What we have to do is actually project a texture onto the points and have a texture that is in the shape of a circle. This is not very easy. So again, let's first generate the texture as an image and connect it to this image display window, that's code that we created before. So again, we need to create a transformer that generates the texture. Its parameters of the transformer will again be a season cell. I feel that generating the texture and applying a circular mask, it's a little bit beyond this tutorial, so I'm going to quickly just enter the code and copy paste it. So again, parents can texture this time. These are parameters. Now we can create a transformer, and with the texture we are creating, it's an array, and the set store is like this, GL text. It will be bound to OpenGL as a texture array, and the number of dimensions will be 2. And then the code I will just copy paste. It's nothing complicated. It's here if you would create an easiest one, just to create a completely filled mask like this, and apply a disk mask over it, and convert it to float 32 if needed. So let's set up the connections. So the radius of the texture 32. You can optionally load the texture from a file, and we want to make it as a float, and we connect the output to this texture. So now let's display it. I mean, this visualization is still displaying these old points that we had. So let's disconnect them and connect the texture instead, like that. And here we see now a disk applied. So now we need to do 2 more things. First, we have to enable the use of texturing in OpenGL. The use of texturing points in OpenGL. The parameter is called point sprite. I will set it like that. Point sprite is true, and then we have to set the actual texture. We have to add it into the vertex shader. Okay, but first you have to define the texture. So let's call the texture as texture, like that. So here we provide a list of textures to give to the program, and we should connect it like that. Texture.connect, and now there will be called p.array as texture. So we connect it, and now, well, the drawing is still here, but OpenGL complains that as texture is not actually being used. So let's actually use that. So for that we have to modify the fragment shader. This is where things are happening. So let's do that. Well, not the vertex shader, but the fragment shader. So we define here high precision, and that we use a S texture, and then we read the color from the texture, and so we know the actual coordinate of our point. We sample it from the texture, and then after that we multiply the frag color with the text color. So let's keep this above, and now you see that all our points suddenly got circular. Let's make the points a bit bigger, we can see it better. There you go. Now you see they're all circular. So the nice thing of such a heavy solution with textures is that it's also easy to make the texture even more fancy. So what we can do, for example, is to randomize the texture a bit. I have to code here. So instead of completely filling it, is to set here a randomly distributed texture. So here you see like that, and now we have a nice added, nicely adding of random points. It's a very nice effect. It's also quite easy to load the texture from a file name using the Python image library, and to use that. So I already defined a cell called file name. Didn't define. Yeah, called text file name, which is empty. But if I set it to some value, and now you see that little orca is inside every point. So this you could use to define well, explosion of fireworks, but more like bubbles. Let's set it back. So let's keep this one. Now it is time to make our explosions look a little bit better. So let's add a uniform that describes the color of the explosion, and let it depend, the intensity of the color, let it depend on the number of points that we have. So therefore we have to generate the gen uniforms parameters. So we gonna get a dependency on n, and let's gonna connect it. Okay, let's smooth again, and then the actual code to define the color. Oh, not the update one. This one. So we do that per explosion. So we calculate an alpha as a function of the number of points. To define the value. Like that. Then we define the hue colors, and for that we need actual current value of the uniforms, which we can get like this. So this defines the uniforms all the time. I have to define them by, of course. So now there's a uniform called hue color, the color of the explosion. Now let's use it in. I'll add it to the uniforms. Hue color, it will be a vec4. We create our window. Let's get it back over here. And now let's modify the fragment shader so that it actually uses the color. So we have it as a uniform, like that. And then all we have to do is replacing this white color with hue color, just like that. And now we have explosions, and every time the color of the explosion is slightly different, or completely different. In addition, we can modify the position of the explosion. Right now it's always in the center, but we can change that. So this uses a new uniform called center position. It's a vec3. So again, this will recreate the window. Let's drag it back. So we have then to use the center position as a randomly generated point inside the gen uniforms code. And it's done just like that. Randomly uniformly distributed position between halfway to the edge of the screen, and we set it as a uniform. But of course we don't see anything happening because we have to incorporate it into the shader. This time it will be the vertex shader. We simply have to add the position. Well, first you have to declare the uniform, like here, and then we simply have to add the uniform's value to the position as it was before. And now we see explosions happening all over the place. You can also add a gravity term so that the balls the points on average they fall down. So again, this will be a uniform in our program. will be a float, and we don't want to generate it randomly, we want to pass it through from a pin, so we create an additional input pin for the gravity. Just like that. And then we create a cell for the gravity. And we set it to 1. Which we do like that. And all we have to do is to update the gen uniforms code to pass it through. So whenever the explosion happens, the current gravity is red and set as a uniform. Now we have to use the gravity inside the vertex shader. So just like that, uniform float u gravity, and gravity affects the y position quadratically. As a function of time. And now you see the punch drop. And finally we can parameterize the point size in the same way, instead of hard coding it in the shader. So again, it would be a uniform in our program. That it would be a input to the gender uniforms, it would actually be an integer. Here as well. And in the code it should be passed through. Like that. Let's create a cell that contains the point size and connect it in the same way. So here point size is 10. So you see the point size still a bit bigger. So we have to update the shader. And the shader is here. The vertex shader. So we have now additional uniform integer point size, and GL point size is equal to U point size. And you see the points are now much smaller. But if we now set the point size to 40, they're very big. Oh, now they're small, and they're small again. And this is a nice value. And a bit of a larger explosion now. So the next step is to change the movement of the balls they all fall essentially in the same way. The relative position between them doesn't change. So we can give them also like a final position as a displacement. And for this we have to define an additional vertex attribute. So right now we have only a single one called value. So let's define one called start position and end position. It's not about uniform. So let me open the vertex data. So right now the code is very simple. So let's now create a bit more complex D type. So a structured NumPy D type, a position consisting of 3 floats and end position, start position and end position, and the data is now n of those structured points, and we have the start and the end. And instead of just creating values, we fill up the start and the end, and then we return the data. So the start positions are the same as they were before, and the end positions, they are now much more diverse. So the points, they will explode much more violently like that. So that's the generation of the vertex data. So vertex data dot value dot 5, for example. So you see all of this start and end has been generated like that. So now we have to modify the program as an additional vertex attribute. So instead of value, we now have a start position, and it comes from the vertex data array, but it comes from an attribute inside. So for this seamless GL program has a field called array. It's called resource access expression, but essentially you just define how you want to access the data, which is in here a start position. Yeah, because essentially if you have here vertex data dot value, you would have here a start position. You see here you get this, essentially the one-dimensional, well, the one-dimensional way of vec3 values, which is what you want. So you need to invoke this expression on the NumPy array before you get the data that you want. So that's exactly what we define here for start position, and we do the same for end position. That. So that means that also you can define your vertex data in any way you like. You could also have made 2 arrays not containing the start position and the end position, and make a list of 2 and not use array but use different array names instead of resource access expression. So the GL program gives you all the freedom. Again, with the GUI it would probably be a lot easier to use. So when we save the program, well, I can show here. You see the points drop because our vertex shader does not recognize these attributes, so they need to be modified. So let's go to the vertex shader. Oh, well, let's keep this one on top. So we don't have anything like value anymore. We have now a start position. And if we change this to a start position, we have our old explosion back, but we can do better than that. Now first let's split things out a little bit. Well, it doesn't matter if you use that or not, but let's do it like this. So now the center position is out of the equation. Again, no real change. But now we do a start position. This is the constant factor, and the thing that changes with time is not the start position but the end position. Ah, we forgot to declare end position. There we go. Now we have a much more explosive explosion, and it looks much more like real fireworks.